Hi, this is Emma Dowd, the Assistant Director of the IUSM Proteomics Core, and this module is going to discuss PeaksX Plus Studio de novo database assisted analysis. So we've already talked about a number of different both search engines as well as integrated proteomic data analysis pipelines such as Proteome Discover. We do typically use Proteome Discover, but we were fortunate enough to be able to purchase PeaksX Plus Studio this past fall, and we were really lucky in that we had a training here at IU School of Medicine in February before all the shutdowns happened. So this is a software solution by a company called Bioinformatics Solutions, Inc., and you can go check out their website. But in essence, it is an integrated proteomics pipeline where you can search DDA or DIA data, and it does have database sequence search and this really special de novo sequencing algorithm, which sets it apart from other data analysis platforms. And we're going to kind of go through some of the other features, which include an extended PTM search and an extended sequence variant and mutation search that are predicated on the ability of this de novo sequencing algorithm. So data analysis. This is similar to any other proteomics pipeline where you need to load and refine your data, do some searching, which in this case includes a de novo search initially, followed by a database search, followed by Peaks PTM, Spider, and quantification. So we'll go into all of these later, but essentially when you are loading your data, this is discussed previously by Dr. Mosley as well as myself, it's really important to understand your instrument parameters and define the cutoffs appropriately in terms of your precursor and fragment ion mass. And if you haven't, you should definitely check out Dr. Mosley's T-Quest HT lecture that discusses that a little bit more in depth. So in this case, I have an example project wizard of how you're loading and creating your project. It will go through a data refinement, which will include looking for what are called feature identification. So this is based on looking at how precursor and fragment ions show up. Do they show up as a peak, for example? And can you transfer that peak to LC data and use essentially a 4D method of identifying a specific peptide and fragment? Then you can go to identification, which following a default de novo search, you can set up a database or a library search, depending on whether you're doing data dependent or data independent acquisition methods. And these are where you need to enter your instrument parameters, again, your precursor and fragment mass tolerance, what enzyme you used, digest mode. I will say that this specific software is actually incredibly useful for situations where you're looking at de novo peptides. That is, if we're not digesting with trypsin, we don't know which amino acids will be present at the beginning and ending of a peptide. And so it's very challenging in terms of a normal database search. But if you're looking at just bioactive peptides, this algorithm can be really helpful. You can also set specific PTMs. So this is analogous to what we do in Proteome Discover, where we can only have up to 6 dynamic modifications. And this is what it is looking for in the database search. Then you can select your database. Again, you can check out that FAFSA database talk by Dr. Mosley. You can also include a separate contaminant database. So you will maybe have noticed that we often combine our contaminants into our specific databases. So we just have one database being searched. But this just has a little bit more flexibility in terms of what you're selecting for specific database, how it's being defined, and what your contaminants are. So then these general options are some of these extra special add-ons that Peaks allow. So I know it's kind of almost forgotten down here at the bottom. So estimate FDR with a decoy fusion database, and then find unspecified PTMs with Peaks PTM. So this will actually do a search on your de novo sequences that looks for any PTM, and I think there's over 300 options. And then you can also do this find more mutations with Spider. So we'll talk about that a little bit coming up. So again, this supports both DDA and DIA technology. and it integrates the database and de novo search to extend your data analysis. And it says they're really focused on resolving these chimeric spectra, and that's when there are multiple peaks that have been selected in a single precursor scan. And generally speaking, we use a really strong cutoff to exclude chimeric spectra because it can be very complicated to match fragment ions back to specific precursor ions. But Peaks uses a slightly different algorithm. And so you can see here, this is kind of the data flow where you have MS1 feature-based identification. That's where I was talking about. It looks for retention time peak. So whether something is an actual feature that exists and coming off a column as a peak. You put it in peaks, and you have your feature data detection, data refinement, and your feature spectrum match. And so this will create this feature file. So this is what Peaks is doing when it's loading your data. And then it goes into this de novo assisted search engine where it starts with a de novo sequencing, very proprietary algorithm. And essentially it's going through these features and looking for anything that could be a peptide. And so this is almost the opposite of most normal database searches, where you have a database and you're searching just the combination of precursor and fragment ions against that database. And you kind of score based on how similar to the possible trypsin digested database peptides your data is. So instead, you have this de novo sequencing that happens before a database search. And then the database peptide search will happen against some of these de novo and feature searches. The good scoring, the de novo tags that have a high score, which we'll cover in the next slide, can then be further searched in Peaks PTM or in the spider function to look for whether you have PTMs or mutations that you might not have found otherwise. So de novo sequencing is when you're deriving an amino acid sequence directly from a mass spectrum. So this is a really new ability. And this was always a weakness in mass spec data in that, you know, if I don't know what I'm looking for, if I have an unsequenced organism, how do I possibly do proteomics on it? If you don't have a sequence, you can't create a database and you can't do a database search. So this allows you an out around it in that it calculates a local confidence score where it's looking for fragments that match the molecular weights of amino acids. And essentially it's going through the different features that have been already defined by the MS1 data and then looking for fragment patterns that could potentially match a peptide. And it will give you these local confidence scores as well as an overall confidence of this quote unquote de novo sequence peptide. And I really recommend some of these papers, especially if you're interested in bioinformatics. So they're still working on some really interesting algorithms for overlapping these sequences if you're sequencing an unknown protein or an antibody from scratch. It can be really useful. So it's then integrated with a database search. So after the de novo sequencing is searched, the high probability de novo peptide sequences are then aligned with protein database entries. So again, this is basically the opposite of what a normal database search engine is doing. Instead, this is really working from the data up, which I think is a great idea. And it allows you to see, so here in blue are high confident, exactly matching peptides that match the database. So what's in gray are these de novo sequence tags that may be non-tryptic peptides, so they wouldn't be found in a normal database search where you're only looking for tryptic peptides. But here, this output is an example of kind of the sequence coverage view where instead of the number of PSMs and highlighted, it's just a very different way of viewing things. But you still have your peptide information, your scan information. These are all things that should be important for you when you're looking in your mass spec data. This is an example of the database search results and visualization. So you'll have a summary where you can filter based on false discovery rate and confidence, protein, peptide, de novo only views of the different data results. So in the protein view, for example, you can click on a specific protein. You will see highlighted the sequence coverage. So that's similar, and it's kind of nice because you can see where there are peptides that overlap. You can also see these gray de novo peptides, and then you can see the different PTMs that were confidently identified here on the right. Down here is this histogram. So this is directly showing you the target decoy and how the false discovery rate was calculated. So obviously the false discovery rate is designed so you have as much positive data with as few false peptides in your data as possible. So if you're having cutoff of say 1%, you'll see this move around, and you can actually see the data change in the different views. So that's kind of nice because it's something you can really directly manipulate in the data view. So peaks PTM. So after the mass spec data has been searched in a database with a limited number of PTMs, so that's how we normally do it. Peaks PTM is an algorithm that will search through for an unlimited number of PTMs. So here's an example of just some really interesting dithiomethyl's. All sorts of different modifications were found on this protein at this specific location. You can see that this is pretty confidently identified because there's multiple PSMs, and it absolutely would not have been seen in a normal database search because you wouldn't bother looking for it. So it's kind of nice that you can find some new patterns perhaps in your samples. Spider is also a really interesting tool. So that happens after peaks PTM, and it's still taking these de novo sequence tags that have high scoring, high scores, and then it's aligning them with your database sequence. And then if it's a little bit off, it will see if it can replace any of those amino acids to quote unquote identify a de novo sequence that matches a protein in your database with a mutation. So it's constructing this real sequence to minimize the sum of the de novo errors. And it's really, really interesting way to find mutations in a set of samples. The visualization for peaks is also very interesting. It's definitely different than previous softwares I've worked with. So essentially, after creation of a peaks project, this will make a very large folder containing all of these different images, and I will be able to zip it and export it, and there will be HTML views, which will be very similar to what you're seeing right here, where there are different proteins that you can click on. It's a really interactive way of viewing things. It will also have this separate peptide view that's, again, an HTML view, essentially of the results that you're getting in Peak Studio itself. So a really great way to look at things. This is an example of that feature map that I was talking about, where you're looking for that retention time specificity. Quantification, it has a slightly different algorithm. I think it's more useful for label-free quantification, but it will show you these heat maps. You can do a lot of editing of your visuals to have specific fold change cutoffs, log-2 ratio cutoffs, looking at your disease and wild type, and you can make some really nice visuals in the quantification method. But I do think that it is a little bit limited by looking at TMT sorts of samples. So this was a pretty expensive piece of software, but we think it will be really useful with specifically patient samples, samples with mutations that may differ from a canonical database sequence, any set of samples where there's a set of PTMs that might not be otherwise identified, especially unsequenced organisms. There's a lot of interesting work being done with microorganisms, with different plants, crickets I've had a submission from, and you just don't know exactly what you're looking for. And also, I think definitely these bioactive de novo peptides where we're not doing any digestion, and Peak's algorithm really provides us a way of identifying those peptides from our mass spec data. I will say that you might guess that this takes a significant amount of time, and it does. And I would say that running a full peak search all the way through Spider on a large project can take 5 days. So you really want to make sure it's relevant to the project at hand before you get into it. But it has a lot of really biologically relevant applications. So I hope you'll reach out if you have any questions, and we'll talk to you at the Q&A session.